Okay, so a quick recap of what we saw before the break. So we were mainly looking at convex sets and their properties. In particular, we defined notions of affine combinations, conic combinations, and convex combinations. These are basically linear combinations where the the coefficients satisfy certain constraints. So in the case of affine combinations, the sum of the coefficients should be equal to 1. In case of a conic combination, they all have to be non-negative. And in the case of a convex combination, they have to be non-negative and sum to 1. Right? And corresponding to these, you have affine sets, cones, and convex sets, which are essentially sets which are closed under the corresponding combinations. Right? But but there's one way to generate affine sets or cones or convex sets out of non-affine or non-cone or non-convex sets by looking at the affine hull. So the affine hull would be the smallest affine set containing your given set. The conic hull is the smallest cone, closed cone, which contains the given set. And a convex hull is basically the smallest convex set which contains your given set. Right? And you can obtain these by just taking all possible affine or conic or convex combinations of points within your given set. And we saw some special cases. We looked a fair bit into hyperplanes and half spaces, and that's particularly useful because of these two special kinds of hyperplanes for a given set or given sets, separating hyperplanes and supporting hyperplanes. So separating hyperplane is a hyperplane which fully separates two given sets. So given two sets, a separating hyperplane is any hyperplane wherein one set is completely on one side of the hyperplane and the other set is completely on the other side of the hyperplane. And we saw that if you have two non-intersecting convex sets, then there's always a separating hyperplane. We also defined the supporting hyperplane for a given set. So that's a hyperplane which touches your given set, but the entire set is on one side of the hyperplane. Right? So it sort of generalizes the notion of a tangent. And in particular, a useful property is that any convex set is basically the intersection of the half spaces generated by the supporting hyperplanes. And corresponding to the hyperplane, we also defined the notion of an extreme point. So an extreme point is one wherein the supporting hyperplane touches your given set at exactly one point, right? Not more than one. So for example, if you had a polytope, then the extreme points would basically be the vertices of the polytope, and that can be naturally seen because if you have a supporting hyperplane, then this intersects the set only exactly at one point, at the vertex. But then if you take any point on an edge or a face, then the corresponding supporting hyperplane would intersect at infinitely many points, right? Okay. And we also saw that it's possible to generate new convex sets from old convex sets. For example, so if you take the intersection of any number of convex sets, then the corresponding set is also convex. The Minkowski sum of two convex sets is also a convex set, and so on. So we looked at various properties of convex sets and how to generate new convex sets from old. And later on, we explored a lot about cones and proper cones in particular. So these are convex closed cones which have a non-empty interior and are also pointed. And the utility was that we could generalize inequalities. So we could define generalized inequalities using a proper cone. For example, we also saw that the set of positive semi-definite matrices forms a proper cone, and using that we can define a generalized inequality. And that is particularly useful because then we can have these general constraints for convex optimization problems. And for a given proper cone, you can also define a dual cone. In fact, for any given cone, you can define a dual cone. But the dual of a proper cone is also a proper cone, and therefore corresponding to a generalized inequality defined by one proper cone, you can also define a dual generalized inequality corresponding to the dual cone. Right? So this is sort of just a brief summary of what we saw before. So all of these convex sets give us a theory of the kind of constraints that we're going to impose on our convex optimization problems. So now let's look at convex functions. Basically, these will be the objective functions that we will want to minimize if it's a convex optimization problem, or we'll want to maximize a concave function. But if you can minimize a convex function, then it's the same as maximizing a concave function. Right. So we've seen convex functions in one variable already in one of the first few classes. And now we'll want to generalize this to higher dimensions. Right. So we will look at multivariate convex functions. So can you recall the definition of a convex function? Yes. Yeah. So f of theta x1 plus 1 minus theta x2 is less than or equal to theta times f of x1 plus 1 minus theta f of x2 for all x1, x2, and theta between 0 and 1. Right. So we'll slightly relax our conditions. So we won't really mind if f is not defined over all of Rn, as long as it's defined over a certain set, which we'll call the domain of f, we are fine. So then we impose this additional constraint that the domain of f is convex, right? Because after all, theta x1 plus 1 minus theta x2 should belong to the domain of f, which means that the domain should necessarily be convex. Otherwise, this whole thing doesn't make sense. So for all x1, x2 in the domain of f, and theta between 0 and 1, we demand that f of theta x1 plus 1 minus theta x2 is less than or equal to theta f of x1 plus 1 minus theta f of x2. Right? So this is the abstract definition of a convex function. But for a univariate convex function, we saw that you can test whether a function is convex or not. There was a necessary and sufficient condition in terms of the second derivative. What was that? So as long as the second derivative of f is greater than or equal to 0 for all x, the function is convex, and this is a necessary and sufficient condition for f to be convex. So we'll look at a similar second derivative test for multivariate convex functions as well, but we'll also look at some other tests which are sometimes equally useful. All right. So, well, we have this function which is a multivariate function, but we'll also see another function. So let's suppose, let's think about the convex function in 3 dimensions. So it's something like a bowl-shaped figure. Yes, please. Okay. So you understand what we mean by the domain of f, right? So it's the set of all x, that the x values for which f is defined. So firstly, we say that f of theta x1 plus 1 minus theta x2 should be less than or equal to f of theta f of x1 plus 1 minus theta f of x2 for all x1 and x2 in the domain of f. Now this definition makes sense only if f of theta x1 plus 1 minus theta x2 is well defined. Correct? For this to be well defined, theta x1 plus 1 minus theta x2 should be in the domain of f. Correct? But by definition, what is a convex function? Sorry, a convex set. So if the domain is not convex, then theta x1 plus 1 minus theta x2 may not be in the domain of f. So this definition can make sense only if the domain is convex, because it has to be closed under convex combinations. That's why we want the domain to be convex as well. Right? Make sense? Okay, so corresponding to f, we'll define a new function g, which is a univariate function. Yes, please.
Specifically, can I say domain of f, say domain of f is convex hull?
Convex hull of what?
Because convex hull is nothing but smallest convex set.
Yes, but smallest. So you define the convex hull of some other set, right? So which other set are you talking about? So are you talking about the convex hull of the domain of f? Yes.
Convex, I'm ready. Same convex hull.
Convex hull of what? So the term convex hull does not make sense in isolation. So you always so the convex hull of some other set is well defined.
Let's say yes.
Let's say.
Yes.
Okay, but what is x? Yes, but again, you need a set to operate on, right? So ultimately what we want is the domain of f to be closed under convex combination. Right? So for every theta between 0 and 1 and for every x1 and x2 in the domain of f, theta x1 plus 1 minus theta x2 should also be in the domain of f. That is what we demand. But that naturally implies that the domain of f should be convex, because f has to be defined in that particular set. Right? So for a given f, we'll define this new function g, which is simply, so g of t is going to be f of x1 plus t times x2. So this g of t is in fact g x1 x2 of t for some x1 x2 in the domain of sorry. So x1 and x2 have to be in the domain of f. And in fact, we only look at those t, so g is defined only over those t for which x1 plus t x2 is also in the domain of f. T is a real number, yes. So x1 and x2 are vectors, so these live in Rn, whereas t lies in R. Right? So in fact, I mean, if you just look at this is essentially a ray shooting out of x1, right? Or it's a line that originates from x1, line passing through x1 and in the direction of x2. Right? So in fact, if you think of f as, let's say, a three-dimensional function, so it looks like a bowl. Basically, what we're doing is cutting out a slice of this bowl, right? So you have this three-dimensional bowl-shaped object. This is x1. This is right. So this is f, and these are the two axes. Let's call them x and y axis. So basically, you pick 2 points, take 1 point, and you cut this function, cut a slice, right? In any direction you please. Take one particular point, right, and take a slice in any direction, right? So you think of the hyperplane which is passing through this. Now, what will the function, what will this slice of the function look like? Will it be convex? Yes. Is the question clear? You're taking this three-dimensional function or function defined in R2, right? So it's a bowl-shaped object. And what you're doing is, depending on x1 and x2, you're just cutting a slice of this. And you're viewing that particular slice. Right? So for example, if you have y f of x1, x2 to be equal, or f of x comma y to be x square plus y square. What I mean by cutting a slice is, let's say I take y equal to 0, right? The set of all x comma y for which y is equal to 0. That's one slice of the function. So now there's only one degree of freedom left over. What does this function look like? Will it be convex? It will be convex, right? So in fact, I can take any slice. So let's say I look at g of t equal to f of x1 plus tx2 comma y1 plus ty2. What does this function look like? So this is x1 plus tx2 the whole square plus y1 plus ty2 the whole square. So this is a function of t, remember. You're fixing an x1 and x2, 2 points x1 and x2, and you're allowing t to vary from minus infinity to plus infinity. Would this function be convex? Yes? No? How many say yes? Okay, how many say no? Okay, what would convince you that this function is convex? How would you verify whether this function is convex or not? Yes? How would you test whether this function is convex or not as a function of t? Take the second derivative. Okay, great. What would be the second derivative of this particular function? So the second derivative would be 2 times x2 square plus y2 square, right? That's an easy check. Now, what can you say about this? What can you say about the second derivative? Right, so it's always greater than or equal to 0, depending on x2, y2. If I take x2 and y2 to both be equal to 0, then it's g equal to 0. It's kind of trivial, but for anything else, it's going to be strictly positive. Right? So this function is convex. But can we say the same thing in general? If f is in general convex, then is g always convex? And vice versa. If g of t is a convex function of t for every x1 and x2, then does it mean that f is also convex? Yeah? Can you speak a little louder? Correct. Yes. I mean, that's intuitively, it's natural to expect. Okay, so let's start with one part. Right? So suppose that f is convex. Then how do you prove that g is also convex? Okay, so let's consider any t1 comma t2 and maybe some theta between 0 and right. What we want to show is that g of theta t1 plus 1 minus theta t2 is less than or equal to theta g of t1 plus 1 minus theta g of t2. Right? If we are able to show that, then it means that g is also convex. Okay, so let's write this out explicitly. What is this equal to? This is f of x1 plus theta t1 plus 1 minus theta t2 times x2. Okay, so we want to somehow get something like g of t1 and g of t2, right? So theta times g of t1 plus 1 minus theta times g of t2, right? But what is g of t1? It's f of x1 plus t1 x2, and g of t2 is f of x1 plus t2 x2, right? So I somehow want x1 plus t1 x1 t1 x2 and x1 plus t2 x2, correct? Anyway, I can get that here. Okay, very good. So let's do that. So since theta is between 0 and 1, I can write this as, I mean, even otherwise, can write this as theta x1. I can write x1 as theta x1 plus 1 minus theta x1 plus theta t1 x2 plus 1 minus theta t2 x2. Right now I'm just rearranging the terms. I'm bringing the terms which have theta as the coefficient, grouping all of those together, and I'm grouping all the remaining terms which have 1 minus theta as the coefficient together. What can I do next? F is convex, so by definition this is less than or equal to theta times f of x1 plus t1 x2 plus 1 minus theta times f of x1 plus t2 x2, which is simply theta times g of t1 plus 1 minus theta times g of t. Right? Yes.
Previous step.
The previous step. You mean from here to here or here to here? From here to here. Okay. Here, f, you know that f is convex, right? So let's call x1 plus t1 x2 to be whatever u1 and this to be u2. And
Why can't we use double derivative?
okay, but then what is the second derivative of f? You need to somehow connect it to f, right? F is convex. Yes. Why? You're taking the derivative with respect to t, right? What property do you know about the second derivative of t? Okay, but there's no, so effectively you're taking the Hessian of f, right? So true, but then you could go that way, but that would mean that you need to prove something else to get this, because you need to study the properties of the second derivative or the Hessian of a convex function of f. So far all we know is that for a univariate convex function the second derivative is greater than or equal to 0, but for a multivariate function we have not shown anything yet. Any other questions? Can a convex function be discontinuous? Yes, it can. Sorry?
Not just on the board derivative.
Yes. So for example, this mod x, it's a convex function. Oh, sorry. I'm sorry. A convex function cannot be discontinuous in the interior. Discontinuous. Yes.
So what if I have like this,
Yes.
except like the bottom point is not at 0 but somewhere down. Is that not one?
It won't, because it's not easy to see, but no matter how you choose it. So talking about something like this, and let's say something like this, right? A discontinuity at this point. It's not obvious, but you zoom in, then you will be able to construct a line, a straight line joining some point here, and at this point of discontinuity, and go on one side, you will be able to get a straight line which is below the function. So a convex function is necessarily continuous, but the first and second derivatives need not exist at all.
So, but at the moment it can-
At the boundaries, it can be discussed. Okay, any other question? All right. So let's. Okay, so I leave the only if part as an exercise, the reverse part. So show that if g of t is convex, for all t, for all x1 and x2, then f is also convex. Okay, so this is something for general functions f, right? Then they may or may not have first or second derivatives. But what if we do have, if the first derivative and the second derivatives exist, that is the gradient and the Hessian exist, right? So we'll first see a first derivative test. Wherein we only know that the gradient of f exists. If the first derivative or the gradient exists, then the function f is convex if and only if the following holds: f of x2 is greater than or equal to f of x1 plus gradient of f of x1 transpose times x2 minus x1. So what is the right hand side? It's basically a first order approximation of the function. In fact, what is it if you take, let's say, f of x to be equal to x squared, just a univariate function? Okay.
So if you start from the point x1, the next one will be the minimum of the function. If you start taking the function from x1.
Okay. So suppose you take a point x. So let's take some point. Let's take f of x equal to x squared. This is x. F of x. And let's take some point, say x1 equal to 1. Right? So what would be f of x1 plus gradient f of x1 transpose x2 minus x1? Okay.
Then in this case, my x2 minus x1 times compared to the value of tangent at x2.
It's actually the value of the tangent at x2. Right. So let's just compute it for this special case. So what would the right hand side be? So remember, you're fixing an x1 and you let x2 to be the free variable, right? So what would f of x1 plus gradient f of x1 transpose x2 minus x1 be? So what is f of x1? 1 plus what is gradient f of x1? 2 x minus 1. And so what would this be equal to? This is 2x minus 1. Can you find the tangent to f at x1? What is that equal to? Yeah. What is 4? No, not f of x2. So what is the tangent to f of x at x1? It is 2x minus 1. So in fact, the right hand side would, for a univariate function, the right hand side would in fact be the tangent. So what this statement is saying is that the function should lie above the tangent at all times. Right? So no matter which point you pick, the function value is always greater than or equal to the value of the tangent at that evaluated at that particular. So this would be f of x1 plus gradient f evaluated at x1, x2 minus x1. So you can pick any x2 you want. The value of the curve will always be above this particular tangent. That's the only statement this is making. Okay, so that's the intuition, but how do we prove this?
Basic definition.
Okay, let's use the basic definition of convexity. So let's take x1, x2, and some arbitrary t. Let's say f of theta x1 plus 1 minus theta x2 is less than or equal to theta f of x1 plus 1 minus, well, I'll maybe do it a little differently here. I'm going to say theta x2 plus 1 minus theta x1 is less than or equal to theta f of x1 theta f of x2 plus 1 minus theta f of x. I just swapped x1 and x2 for special reason. Okay, so can we bring this to a form, to this particular form? So let's take f of x2 to one side and put all the other terms on the other side. What do we get? What do you have on the right hand side? It doesn't have to be in the form that we want finally, but what would you get? What would the expression look like? Yeah. Okay, we've not got to that yet, but we will get something like that. But what is it equal to? So it's equal to whatever 1 minus theta minus of 1 minus theta f of x1 plus f of theta x2 plus 1 minus theta x1 whole divided by theta, right? So let's isolate one term containing f of x1. So I have theta times f of x1 divided by theta. So that is just f of x1 plus I have f of theta x2 plus 1 minus theta x1 minus f of x1 divided by theta, right? This is f of x1 plus, I can write this as f of x1. I want to write this as f of x plus delta x, right? So this is f of x1 plus theta times x2 minus x1 minus x1 divided by. So we looked at a similar expression when we studied the gradient. What is, as theta tends to 0, what does this tend to?
So you can
Yes,
divide and multiply by x2 minus x1.
then multiply and divide by x2 minus x. Well, x1 and x2 are vectors here. So you can multiply and divide by x1 and x2. If they're univariate functions, then that's fine. But in general, you can. But we know that as theta tends to 0, this quantity tends to the gradient transpose, the inner product between the gradient and the direction. So this is the direction x2 minus x1. Right? So this is f of x1 plus gradient of f evaluated at x1 transpose times the direction, which is x2 minus x1. Right? Any questions? Okay, so now suppose we want to prove the other way around. So we have f of x2 greater than or equal to f of x1 plus gradient f times x2 minus x1 for all x1 and x2. Then how do we show that f is also convex? reverse? Can you just do that directly? How would you go reverse? Okay, so ultimately, suppose we wanted to show that f is convex. You need 3 points, right? You need an x1, you need an x2, and you need another point in between x1 and x2. Uh, and you need something which relates the two. Okay, how do you do that immediately? Well, we have what we need is right before us, right? We have f of x2 greater than or equal to f of x1 plus gradient f times x2 minus x1. Right? So let's take 3 points. Let's say that z is equal to theta x1 plus 1 minus theta x2. Okay, so we have z and we have the points x1 and x2. Right? So let's look at f of x1. I can write this as f of x1 is greater than or equal to f of z plus gradient of f evaluated at z transpose z minus x1. Right? And I can also say that f of x2 is greater than or equal to f of z plus gradient f of z transpose z minus x2. So what do we want to finally show? We want to show that f of z is less than or equal to theta f of x1 plus 1 minus theta f of x2.
Multiply with theta and 1.
Okay, so let's multiply the first inequality by theta, the second inequality by 1 minus theta. So I get theta f of x1 plus 1 minus theta f of x2 is greater than or equal to theta f of z plus 1 minus theta f of z, which is simply f of z, plus some other term. So this is gradient f of z transpose times theta z plus 1 minus theta z plus minus theta x1 minus 1 minus theta x2. So gradient f of z is common to both these terms, right? So it's theta times this plus 1 minus theta times this, which is the same as gradient f times theta times this plus 1 minus theta. But what is this quantity? This is just z minus theta x1 plus 1 minus theta x. That's just z, right, by definition. So this is also z. So I have z minus z. So this whole quantity is 0. And here I have just f of z. Any questions? So this is sometimes a useful test, but it's also sometimes a useful property. If you know that the function f is convex, then this property can sometimes be very useful. So this is something that you might have seen before, and that is, so suppose that the Hessian exists. So recall that the Hessian is a matrix, an n by n matrix. So f is convex if and only if the Hessian is positive semi-definite for all x. The useful way to show this is using what we already know for univariate functions. So it's helpful to connect the Hessian with the second derivative of the univariate function f of x1 plus t x2. So there's something that was suggested for to prove the connection between g of t and f of x. But let's try looking at the second derivative. So suppose that g of t is equal to f of x1 plus t times x2. So this is f of x. So what can you say about the first derivative of g? So this is just g of t plus delta as delta tends to 0, g of t plus delta minus g of t whole divided. But
wouldn't it be the gradient function?
which one?
And this is the gradient dot product.
We want to show that. That's it. But what is that in terms of f? Right. So this is f of x1 plus t plus delta times x2 minus f of x1 plus tx2 divided by delta x1 plus tx2 plus delta x2 minus f of x1 plus tx2 whole divided by delta. What is this equal to? So always remember, if you have a function f, a multivariate function, and you have f of x plus ty minus, or f of x plus delta times y minus f of x divided by delta. So as delta tends to 0, this tends to the gradient, the inner product between the gradient and y, right? The coefficient of the, whatever the term multiplying the delta. So in this case, what is this going to be equal to? So it's going to be the gradient of f evaluated at x1 plus t times x2 inner product with x2, right? Okay, so that is good. So now on similar lines, what is the second derivative going to be equal to? So it's limit as delta tends to 0 of g prime of t plus delta prime of t divided by delta. So I'll write this. This is also equal to x2 transpose gradient f x1 plus tx2, right? They're both the same thing, but I'll prefer to use this particular form. So what will this quantity be?
Derivative.
Yes, so it's just going to be x2 transpose times the double derivative or the Hessian of f evaluated at x1 plus tx2 transpose x. So because that this is a matrix, right? So this is the form x2 transpose some matrix times x2. Yeah. So if g double prime of t is always, so let's just write that down. So the second derivative of g with respect to t is equal to x2 transpose the Hessian times x2. I can take the transpose on the right side as well. One second. Sorry, oh, del square. Well, I can. What if I take the transpose once again on the right hand side? What do I get?
The way another is symmetric.
Sure, it's a symmetric matrix. So suppose that the Hessian is positive semi-definite. Then what can you say about G double prime of T? It's always greater than or equal to 0, right? Because X transpose Hessian X should be greater than or equal to 0 because the Hessian is a positive semi-definite matrix. Okay, so that proves one way. Now, if G double prime of T is greater than or equal to 0 for all T and for all x1, x2, then it means that x2 transpose the Hessian times x2 is always greater than or equal to 0 for all x2. Which means that the Hessian should be positive semi. Any questions?
Both.
It shows both directions. Yes. So, and similarly, if f is convex, then so is G. Which implies that G double prime of T is greater than or equal to 0. X2 yeah. Okay, so now let's try to use the second derivative test, right? So what about linear functions? So f of x is equal to sum A transpose x plus b. what is del square f equal to? It's the zero matrix. Which is PSD. Let's take a quadratic.
Will it be x plus x zero matrix or x plus
It's going to be a matrix. Hessian is always a matrix, right? So the ijth entry is simply dou square f by dou xi dou xj. Correct?
A is PS,
Sorry?
B is PS,
So f of x is it's for an arbitrary a. It's defined now for an arbitrary a. What is the gradient? What is Hessian? What is the gradient of f equal to?
A plus A transpose.
It's a plus a transpose times x. So what would the Hessian be? Yeah, it's just a plus a transpose. And when is this PSD? It's always symmetric. Certainly, when A is PSD, A plus A transpose will also be PSD. But does A have to be PSD for A plus A transpose to be PSD?
A plus A transpose function.
Is that enough? Why? Is it guaranteed to be PSD? So suppose A is minus the identity matrix. What is A plus A transpose? Is it PSD? So what is X transpose A plus A transpose X going to be equal to? Yeah, correct. So it's just going to be 2 times X transpose AX. So if A plus A transpose is PSD, then it means that X transpose A plus A transpose X is always greater than or equal to 0 for all X. Correct? Which means that X transpose AX should also be greater than or equal to 0 for. So A should be PSD. So X transpose AX, this quadratic, it's a convex function only if A is PSD. right? So let's take another function, f of x equal to e raised to a transpose, which is e raised to summation equal to n aj x. What is the Hessian going to? What is dou square f by dou xi? Sorry, f of x times a ai times aj. Does everyone agree? So this is also equal to product j equal to 1 to n e raised to aj xj, which is probably easier to work with. What is the partial derivative of this with respect to, say, xj? Yeah. Okay. Why? Times what? aj times ai times. There's one more term missing then. If you are taking the product of j not equal to I. Look at dou f dou xi. So this is product j not equal to I of e power ajxj, as you rightly pointed out, times dou by dou xj xi of e raised to aixi. What is this equal to? So this is ai times e power aixi, right? But then I can multiply this along with this. So this is just ai times f of x. Okay, so what is the ijth entry of the Hessian matrix? Yeah. Just AI AJ times f of x, right? So what you can write this in a neat form. IJ in terms of the vector A and f of x.
A transpose.
A transpose, f is a number, right?
Not like that.
Yeah, so it's just the outer product of A with itself. So it's A transpose times f of x.
Path always pays zero.
Yeah, so this is always, yeah,
Oh, it's oh,
f of x is always positive. Yes, is this a positive semi-definite matrix? It is, right? Simply because if you look at x transpose A transpose f of x, produce something else. From y transpose this y, then this is just y transpose A the whole square times f of x. We know that this quantity is always greater than or equal to 0. And f of x, this is also greater than or equal to 0, right? Because it's an exponential function. This is always strictly possible for all x. Okay, so I'll leave you with an exercise. What about f of x equal to the p norm of x? So this is 1 to n xi raised to p whole raised to 1. Any questions? Sorry? Is the mod?
does the mod not match?
Um, the mod does matter. So, okay, to begin with, you can prove it for even p, where the mod is not required, but you don't necessarily have to use the second derivative test. Right? So let's stop here.